Hi everyone, welcome to our first tutorial in Thermo 2. Today's tutorial is going to focus on chapter 7 as well as chapter 8 in your thermodynamics book. Chapter 7, which is known as or which is called entropy, and chapter 8 is exergy, which are two opposite ideas. So what is entropy? So entropy in general is a measure of randomness or disorder within the system. Or in other words, you can say it's a quantitative measure of microscopic disorder of in a system. And what is exergy? Exergy is maximum potential to do work, or measure of work potential, you can say, or maximum energy available to do work. That is known as exergy. Or it's also known as the useful work potential for a given amount of energy at a specified state is exergy. Okay, the available energy or available work. So summary of chapter 7. In chapter 7, you have seen what is entropy, increase of entropy principle, entropy change of a pure substance, isentropic processes, entropy change of a pure substance as well as isentropic processes. You also have seen the property diagram involving entropy. You have seen what is entropy, the TDS relation, entropy change of liquid and solids, entropy change of ideal gases. And right now in Thermo 2, you have seen reversible steady flow work, as well as you have also seen the minimizing the compressor work, and you have seen isentropic efficiencies of steady flow devices and entropy balance. Okay, so that was the summary of chapter 7. And in chapter 8, you have seen about what is exergy. We also known as exergy is the maximum work potential or maximum useful work you have. Okay, energy you have to do work. Exergy is the work potential associated with kinetic and potential energies. You have seen about the reversible work and irreversibilities. You also have knew what is second law of efficiency. Then exergy change of a system, exergy change for a fixed mass, which is known as closed system, and exergy of a flow stream, which is an open system. And you have also seen exergy transfer by heat, work and mass. Then decrease of exergy principle and exergy distraction. Then exergy balance for a closed system, exergy balance for a controlled volume, as well as exergy balance for steady flow system, reversible work and second law efficiency of steady flow devices. So that was the summary of chapter 7 as well as chapter 8, okay, which you have learned in detail in the lecture with the professor. So right now I have taken two good examples or two important questions which is related from chapter 7 as well as chapter 8. So this tutorial is going to focus on these two important questions from chapter 7 and chapter 8. That doesn't mean these are the only two important questions. There are also many important questions, but I have taken two important questions which I felt is covering most of the topics from chapter. The question that is going to cover most of the topics from chapter 7 is there in this question. So that is the reason why I have chosen this question. So let's start with the question. What is given in the question? Air is compressed by an adiabatic compressor. It is given adiabatic compressor. Okay, so that word you should make sense. It is given it is adiabatic compressor. From 95 kilopascal and 27 degrees Celsius to 600 kilopascal and 277 degree Celsius. Okay, so you will take down the temperature, the pressure and the initial temperature and the final temperatures. So let's write down P1 is equal to 95. Okay, any question always write down what are given. 95 kilopascal and T1 is 27 degrees Celsius. Okay, and what is also given to you? P2 is given, which is 277 degrees Celsius, and sorry, this is T2. Okay, the T2 is 277 degrees Celsius, and P2 is what? P2 is given to be 600 kPa, kilopascal. Kilopascal. Okay, so state 1 and state 2 are given. Assuming variable specific heat and neglecting the changes in the kinetic and potential energies. So neglect the changes in the kinetic and potential energies. So it is given adiabatic system, and what is also given? Air. So what is air? Air is an ideal gas. Okay, with variable specific heat, that is also given to us. Okay, what is the question asking us? And he also said kinetic energy equal to potential energy is negligible, means you can consider it as 0. That is also given to us. Kinetic energy and potential energy is negligible, so it is equal to 0. So what is given to us? Determine the isentropic efficiency of the compressor. Isentropic efficiency of the compressor. Then what else you need to determine? Isentropic efficiency of the compressor as well as the exit temperature of air if the process were reversible, and the exit of the compressor if the air were reversible. Okay, so first what you will do, what is given to us? The temperatures are given to us. So as well as the pressures are also given to us. So we need to find the properties with respect to these temperatures and pressures. Okay, so what is given to us? For us, the temperatures and the pressures at two states are given. Okay, so let's first draw the TS diagram. Okay, let me draw the TS diagram. Okay, but the entropies are unknown for us, but temperatures are known for us. Okay, so before we do that, let me erase it. Before we do that, let's go to the property table, which is table A17. Table A17. Okay, so let's go to the property table, table A17, and find out the H1 and H2 corresponding to this temperatures. Okay, so T1 is what? T1 will make it as 27 plus 273, so which will give you a value of T1. If you convert it to Kelvin, it will be 300 Kelvin, and T2 will be how much? T2 will be 550 Kelvin. So right now I have changed T1 and T2. So now I will move to the table, which is table A17, because we are dealing with air, ideal air. So H1 with respect to this one, enthalpy for at 300 degree Kelvin was around equal to 300.19 kilojoule per kilogram, and H2 was around 554.74 kilojoule per kilogram. Okay, these are the H's we found, and we will also find PR1 from the table. So PR1 is equal to 1.386. That is also found. Okay, so why did we find PR1? Now we will use the formula, which is PR2. For isentropic, the enthalpy of air at the end of an isentropic compression process is determined using one of the isentropic relations of ideal gas. Okay, so since we are having ideal gas, we can use this relation. PR2 is equal to PR1 multiplied by P2. P2 is the actual pressure, okay, over P1. Okay, so what we know what is PR1. PR1 is what? 1.386. Okay, also we know P2 and T1. P2 was what? P2 was 600 kilopascal. So 600 kilopascal, 600 kilopascal divided by, and P1 was what? 95 kilopascal. 95 kilopascal. Okay, so now we have PR2, which is 1.386, the PR1 multiplied by P2 over P1. With this, you can find what? You can find PR2, which is around 8.754. This is your PR2. Okay. Now using this PR2, because we got it, let me take this up here for you so that we have a space over here. We got PR2 is equal to 8.754. Okay, so now with this respect to PR2, we will be able to find the H2S is equal to, because the one we found over here H2A actual. Okay, we need to find the ideal one or the isentropic one, isentropic enthalpy. So that is around, we will get it around 508.7. All these values I have taken from the property table. So I hope you know how to do interpolation as well as how to read the values from the property table. Okay, so since this we are already covered in Thermo 1, I am not explaining it over here. So if you have any questions, we may discuss this in detail in the live session. So we have found the H2S right now. Okay, so now you have the H1. Okay, we have the H1, which is we found from the table to be 300 kilojoule per kilogram 300.19. okay, that is 19, so there is a small error I made. 300.19 kilojoule per kilogram. Okay, so this is the H1 we found, and we have H2A, which is around 554.74 kilojoule per kilogram, and we have H2S, which is around 508.72 kilojoule per kilogram. Okay, now we know, because for a compressor, what is the minimum one? We know it is the isentropic one over the actual, right? Because isentropic one will be the least work given. Because what is compressor? Compressor is the work consuming device. Turbine is a work producing device. So always isentropic one will be the least one taking the one you need to give power, and the more one that will be giving output, because that's how you will make the difference between compressor and turbine. Okay, so since we are having a compressor, the isentropic efficiency for the compressor is equal to the H2S minus H1 over H2A minus H1. Okay, why did I do that? Because for a compressor it is isentropic compressor work divided by the actual compressor work, okay, which is also written as Ws over Wa, okay, which is equal to the values we have over. What is H2S? 508.74 minus, what is H1? 300.19 divided by, again, numbers without unit doesn't make any sense, so you should be very careful about this. Kilogram divided by the actual compressor work, which is 554.74 minus 300.19 kilojoule per kilogram. So isentropic efficiency, if you calculate, I found it out to be 0.818. Okay, if you multiply by 100, you will get 81.9%. So that is about how we find the isentropic efficiency. Now the part B of the question was what? It was to find the exit temperature of the air if the process were reversible. To find the exit temperature of the air if the process were reversible. Okay, so in this case, what they are asking you to find the isentropic temperature. That's it. In a simple word, it is reversible means what? Isentropic process. We knew H2S is what? Is 508.72 kilojoule per kilogram. So with this enthalpy, you will get T2S has 505.5 Kelvin, and if you convert it to degree Celsius, or you can keep it in the Kelvin, 506 Kelvin. So that is the exit temperature of the air if the process were reversible. So this was a quite easy, nice question, but the most important principle of this question was what? Is to understand the isentropic efficiency of steady flow devices. So this device was a compressor. So it is a work consuming device. Turbine is a work producing device. And similarly, there is also isentropic efficiency for nozzle and as well as pumps. So now let's move on to the next question, which is from what do we have over here? Again, we have a compressor. Since I like compressor, that's the reason I took questions from compressor. Air is compressed steadily by 8 kilowatt compressor. So power of the compressor is given over here to you. Power is given as well. So for any questions, you will write down what are the given. So P1 is equal to 100 kilopascal. And T1 is equal to 17 degrees Celsius. When you convert into Kelvin, you will get 290.16 kilojoule. sorry, 290 Kelvin. Kelvin, it was Kelvin, okay, 290 Kelvin. 290 Kelvin. Similarly, what is given? 600 kilopascal and 167 degrees Celsius. So it is compressed from this pressure to this pressure. So pressure to P2 is 600 kilopascal and T2 is 167, and then you convert it to Kelvin, you will get it around 440 kilopascal. And again over here it is ideal gas or air. So we will go to property table A17 and find out the properties, which is H1 and S1. So now I will find out H1 and S1, which I found from the property table to be around 290 kilojoule per kilogram, and S1 has 1.6802 kilojoule per kilogram Kelvin. Similarly for this. And similarly H2 and S2. So this is the inlet state and this is the exit state. So we found H2 and S2 has 1.69 kilojoule per kilogram, and S2 has 2.0887 kilojoule per kilogram. So H1, S1, H2, S2, everything is fine found. Okay, the entropy change. So now what we will do, we will find the exergy. We are dealing with exergy, right? The exergy change of the air during the compression process. So that is what we are going to find. The exergy change of the air during the compression process. And again here it is specified, neglect the changes in the potential and kinetic energies. So first let's write the equation. Delta psi is equal to psi 2 minus psi 1, which is also equal to, we know, H2 minus H1. Since we are dealing with flow devices, so it's enthalpy minus T0 into S2 minus S1. S2 minus S1 plus the kinetic energy and the potential energy, which is 0. So plus kinetic, which is again 0, I am not writing it down, and the potential again plus the potential, which is again 0, because they told us to ignore it. So if I write it as like this, I'll get H2 minus H1 is already known, and my temperature is, surrounding temperature is also known. T0 is surrounding, which is 70 degrees Celsius, which I will convert into Kelvin. And after substituting everything, but S2 and S1 are not known to us. S2 and S1 are not known to us. So we know that S2 minus S1 is equal to what? S2 power 0 minus S1 power 0 minus R ln P2 over P1. So from here we can find S2 minus S1. Okay, all these values I have, S2 0 I have, S1 0 I have, R value is the universal gas constant which we already have. P2 and P1 also we have. Okay, with that I will get the delta S2 minus S1 as 0.09356 kilojoule per kilogram Kelvin. So we found S2 minus S1. We have it now. It's clearly we have it. Okay. So now we can find the increase in exergy or the change in exergy, because we have all the values right now. I'll substitute into this equation, which is delta psi is equal to, we know it is nothing but H2 minus H1 minus T0 into S2 minus S1, which we already know now, S1. Okay, into S2 minus S1, which will give me the value of 178.6 kilojoule per kilogram is the increase in the exergy. Okay, now what is the second part of the question? The second part of the question is asking us to the rate of exergy destroyed during this process. What is the rate of exergy destroyed during this process? That is the second part of the question. So exergy distraction is minimum reversible work in, right? That is the exergy distraction we have. So we write it as reversible work in is equal to mass flow rate is given to us pi 2 minus pi 1. Okay, so the reversible work in and the minimum work input that need to be supplied to the compressor per unit mass of the refrigerant, unit mass of the air. So the mass flow rate is given to us, which is around exergy distraction, or you can also take it as the minimum work input needed to be supplied to the compressor also. Okay, so what is given to us, the mass flow rate is given to us as 2.1 kilogram per minute. It's given in minute. Okay, so you have to change it into a second. That is your duty to change this kilogram per minute into second, because we know 1 minute equal to 60 seconds. So if I want to change it to second, I will divide by 1 minute down and multiply by 60. Okay, into 1 minute over divide by 60 into this value we already have, which is 178.6 kilojoule per kilogram. With this we will get the minimum reversible work in as 6.25 watt. Okay, so that was about this two questions. So thank you, and if you have more questions regarding this tutorial, we will explain it in detail in the live session. Thank you.